Opportunity to speak here, and thank you very much for being here to listen. I just want to share with you some modelling that we did, trying to understand what use and value body condition score can be for some commercial dairy farmers who are interested to know how much they should really try and hit those body condition score targets for our seasonal systems. Okay. I can't get my mouse to work, I'm sorry. Nope, nothing at all. That's great, thank you. So, as you've heard, we have a seasonal dairy farming system, and like all seasonal dairy farming systems, essentially we're trying to harvest the capture of grass and turn it into milk in order to make some return. And to do that, we need to have, it's still not going, we need to have a tight calving pattern and a tight mating pattern. No. Thank you. My mistake. So we need this tight calving pattern, and so we need a very efficient reproductive process. And we measure that in terms of our 6-week in calf rate, as you've already heard, because essentially what we're trying to do is match pasture production with feed demand from the cows and from the herd. So we mate over a short period of 10 weeks or so in order to calve over a short period so that we can get that mismatch between herd demand and feed production as small as possible. And we measure our success in that way in terms of our 6-week in calf rate. And this is some data from last year for the national herd, looking at the percentage of the herd that's pregnant by 6 weeks of mating. And you can see that most of our herds are well below the 78% target for 6 weeks. Only about 15% are currently making it. And the study farms in this particular trial were lower than that. They were around about the 60-65% for their 6-week in calf rate. So what drives this is submission rate and conception rate, and as you'll know as working vets, the easiest one to manipulate in this context is the submission rate in the first 3 weeks. So this is the area that we looked at for our farmers. So the next question was, how well are we doing in terms of submission rate? And this is the last 9 years of the national herd submission rate, and we're looking for a target of 90%, and over that 9 years, the average has been 80%. And again, our study farmers were slightly worse. They were around about 76%. So if we could manipulate this submission rate, we could potentially make some really big gains. We have a national average conception rate of 52% at the moment, and if we were able to raise that submission rate just by 10%, then just about 3/4 of our herds would hit that target for the 6-week in calf rate. So what we wanted to know really was, can we do this? Can we predict which cows are going to get served and which cows are not going to get served from data that we can capture on commercial dairy farms? And when we've looked at those predictions, can we use some new techniques to improve them so that we get better accuracy? And then lastly, is what we're collecting and measuring actually really driving those submission rates for those farmers, and is it going to be worth their while in terms of hitting those targets? So we had 10 commercial dairy farms with about 8,500 cows. They're all seasonally calving, pasture-based production systems, and after we got rid of the dirty data and the carryovers and so on, we were left with just over 8,000 cows to use. None of these herds used any form of hormonal intervention for their reproduction, so they all mated just on observation with no hormones. My colleague, Bernie, scored all these cows multiple times every month, which is a huge job, and she's an accredited body condition scorer, and she uses the Dairy NZ system, which has been developed by John Roche and others, which essentially, on a working farm, we experience that we get cows between 3, which is down the skinny end, and cows at 6, which is towards the fat end. And essentially, we're looking for a 5.5 foot calving. So for each farm, we collected all this data on the body condition scores, and then we got as much demographic data out of the databases as we could. And we also were lucky that these herds herd tested once at mating time, so we were able to get milk production stuff as well. And then the modelling, we used 2 different techniques, and I'll explain a little bit why we did that. Firstly, we used a multivariable logistic model. It's relatively straightforward, and it's been done before, which meant that we can compare what we find with what's been published, and so we get a feel for whether what we're finding is comparable to other people. It also allows us to quantify those relationships in terms of odd ratios, and that's quite useful. It means we can say, well, we think this is doing this, and this is how much it's doing it. But the records do have to be complete. If we have missing data, those rows in the spreadsheet really can't be put into the model. And if you want to model interactions, and there are often lots of interactions in a data set like this, it gets quite complicated. You have to do it explicitly, and understanding how those interactions work can get quite confusing. And moreover, it has some requirements of the data, particularly that there isn't too much collinearity in the data and that the associations are broadly linear. And that's often not the case in large data sets derived from farms. So we wanted to see whether we could get over some of those handicaps by using some different methods. And so we used machine learning. It's less familiar, certainly was less familiar to me, and it doesn't give you a quantifiable result. Essentially, it either bashes the data to bits using these algorithms within the computer, or it coaxes the information out of them, depending on which kind of machine learning model you use. But essentially, it doesn't tell you a number of the effect, but it does allow you to predict and to classify data. There are fewer examples to compare with in the literature, so it's a little bit more difficult to know whether what you're finding is comparable. But the big advantages for us is it's very comfortable with missing data values. It can cope with those. And some of the systems can model interactions really nicely and in a really comprehensive way. Also, it's tolerant of the vagaries in the data of collinearity and non-dependency of relationships and non-linear relationships. And so it has some advantages. And we use 4 fairly common machine learning algorithms to analyze our data as a comparison. So what we were wondering basically is there something that we can't detect with the logistic approach going on in this data set? And if we use these alternatives, will we get a clearer answer of what's going on? So essentially, we were confident that there would be confounding and there would be interactions. This is just a very simple example of one. And we were asking, would the machine learning techniques handle that kind of situation better? So these are our results very quickly and briefly. Essentially, our herd's performance was as follows. We had a submission rate of 77% for that season and a 65% in-calf rate at 6 weeks. So less than industry standard, but very normal. This is their body condition score profile. So we're looking to calve at 5, and these cows are calving down a little bit light. They all hit nadir at 51 days after the planned start of calving. And they calve at 4.4, they lose about half a body condition score to the lowest point nadir, and then they gain about 0.3 of a body condition score a month afterwards. So 65% of those cows are hitting nadir before the planned start of mating. So what does our model, our logistic model, tell us about submission rate in terms of body condition score? It's one of the advantages of the logistic model. We get some odds ratios. So essentially what it's saying is up to a body condition score of about 5.5, there's an advantage in terms of your submission rate if you calve at those body condition scores. But once you calve over 6, your submission rate tends to fall. Fat cows don't cycle so well. That fits your own experience. The lower the body condition score at nadir, the worse in terms of submission rate. And the more you lose in between those 2 points, again, the worse it is for your submission rate. Interestingly, the faster you lose that body condition score, the better. You're more likely to get served if you lose it quickly. And this means that if your nadir occurs before the planned start of mating, again, you're more likely to get served. Oops. Sorry. So we've got some interesting p-values. We've got big numbers, so we get small p-values. But what do the variables actually mean in terms of what's going on? How much are they driving that submission rate? And there are various different ways that you can do this with all the models that we looked at. And they vary slightly depending on which model you look at. But across the board, body condition score overall is about responsible for 25% of the variability in the submission rates that we're experiencing. And importantly, days calved at planned start of mating is responsible for another 25%. Again, that makes sense with our own anecdotal experience. So we've got some models, we can predict some stuff, but what we really want to find out is how good those models are. And we use a couple of techniques to do that. One is discrimination and the other is calibration. And discrimination is essentially saying how good is the model at saying that's a cow that's going to be served, and how good is the model at saying that's a cow that's not going to be served. It gives us values of sensitivity, specificity, PPV and NPV and stuff like that we're fairly familiar with. Those values are threshold dependent. It depends on what probability we choose to say that's going to mean that cow gets served. So we can also look at the area under the ROC curve, which is threshold independent. But essentially that's looking at the models in the same sort of way. How good are they at classifying? The other way we can look at the models is a stochastic way, which is in terms of their probability. If our model predicts that 70% of this group of cows is going to get served, do 70% of that group actually get served? And does that change with the predicted probability? Are we better at predicting high rates than low rates? So we looked at these things in 2 different ways. And just as an aide-memoire for me, we do this on a testing data set, which is different from the training data set, so that we make sure that we are actually testing the models in a real-world situation. So this is a horrible slide, giving you a lot of figures. The ones I want to concentrate are the ones in red, which I tend to think of most as a clinician. So this is 3 of the models, the logistic, the neural network, and the random forest. The other 2 were not as good, and that's partly why they're not here, but they weren't that different. The first thing to take away from this is that none of these models is sparklingly brilliant, and that was my first big disappointment. I really hoped that some of them would be wonderful, but they're not. Looking at the PPVs and the NPVs, just to summarize it, essentially there's no difference between these 3 models. They're all performing in very much the same way. And what it basically means is that most of the cows that we predict to be served will be served, but unfortunately, more than half of the cows that the models predict will not be served actually do get served. Okay, so it's good in one way, but not in the other. So, first question to answer was, no, they don't. Our machine models are not necessarily an improvement in this way compared to the logistic model. But none of the models is that good. But trying to sort of defend that a little bit, actually they're no worse than many, many models have been published. With rock values exactly the same, we've seen good models published, and this is in line with what's been found by other people. So here's our rock curves, and again, those 3 graphs at the top, there's no real difference in the confidence intervals. Technically, the neural network and the logistic are slightly better than the others, but in a meaningful way, there's no real difference between them and the random forest plot. None of them are that great. The area under that rock curve is 0.75, so it's better than guessing, but really what we want is a rock curve, as you'll know, way up here, nicely out to the left-hand side with an area under the curve of 0.8, 0.5, 0.9, that sort of thing, and we're just not getting that. So none of the models is brilliant. Okay, just wrapping up, the last way we looked at the models is in terms of calibration. So, okay, we've looked at the deterministic way of looking at those models, how good are they as classifiers, and now we're trying to say, how good are they in a probability sense? If we predict 70% of the cows are going to come on, do 70% of that group come on? So we look at that by comparing the predicted probability along the x-axis with the observed true proportion up the y. And essentially, we want most of our data points lying on that 45-degree line. And you can see that to some extent we do get that, but not at low probabilities. All the models are performing less well at the low end of the probability scale. So at the high probability scale, they're doing pretty well. If we predict a cow is going to come on, she does come on. So that lines up with a discriminate way of analysing this data. But on the other end, if we say she's not going to come on, some of them do get served and some of them don't. So our models are not so reliable down that low end. So overall, what does this tell us, and was it worth it? Well, yes and no. It taught me an awful lot about machine modelling, and it satisfied the inner nerd inside me. But we can make some reasonable models about predicting which cows will get served and which won't. But we're tending to over-diagnose the non-cycling in our models. So I have to ask, why aren't they better? Because I was disappointed. I really hoped that I'd be able to stand up here and show a lovely rock curve with a big area under the curve, and the machine models would have done it. I think certainly I could put more variables in there. I restricted my data set because I wanted to have a common data set for all my models, so I couldn't have missing values. And if I had more variables, I might have captured more of that variation. But I think more importantly, there's a lot of farmer error in which cows are served and which cows are not served. They make both false positives and false negatives. And so they put cows up that are not on heat, and they don't put cows up that are on heat. So my gold standard of submission rate is not really a true gold standard. And so the models may actually be better than we think they are because our data that we're calibrating them against has got this innate inaccuracy in it. And lastly, could there be unknown, complicated data relationships going on? And that was one of the things I originally wanted to find out. And my conclusion is no, probably not, because all the models are essentially giving me the same results. And some of these models, like the random forest and the neural networks, are really, really good at understanding the complexities in the data set and teasing out all the hidden interactions and confounding that's going on. And yet they're producing very much the same results as I'm getting with the logistic and the decision tree models. So I don't think there's a hidden thing going on. So that was useful for me to know. Okay. The other thing is that the machine models, although we all use this common data set to make an easy comparison, they don't need to know what the variables mean. They don't need to know body condition score at nadir or body condition score at calving. They just need a number. So they can work in real time. Whereas the logistic model, I had to go through and calculate what nadir condition was, what body condition score at calving was. So machine models can work in real time, and so potentially, cow-side, these techniques could be used to help farmers make decisions on farm. I'd like to wrap up with a thank you for listening. A big thank you to Bernie for scoring all those cows. It was an enormous job, 43,000 individual scores she did. A very big thank you to the farmers, and a huge thank you to the people who've produced R and put it together and have made the packages that allowed me to do what I've done. Thank you very much.